And with this, we're actually moving towards the part of the workshop where we discuss the visual localization challenges. So we're going to have 3 talks this morning. The first one is a talk by Paul-Edouard Sarlin, who won actually all 3 localization challenges. Then afterwards, we are going to have a talk by the runner-up of the handheld devices challenge, which will be given by Sudong Chang. And then the talk from the runner-up on the local feature challenge, which will be given by Yaroslav Melekov. And with this, I'm going to hand over to Paul-Edouard.
Thanks, Torsten. Let me share my screen. Let's see. All right, you should be able to see my screen now. Let me know if you don't. So hi, everyone. My name is Paul-Edouard Sarlin. Thanks, Torsten, for the invitation and the introduction. So I am a PhD student at ETH Zurich in the Computer Vision and Geometry Lab, and I am here to talk about hierarchical localization with our toolbox HLOC and SuperGlue, which won the first place in 3 challenges presented in this workshop. So our submission builds on top of 2 of my past works. HLOC is a toolbox for visual localization that we open sourced last month. It was developed here at ETH Zurich with the support of Mihai Dusmanu, Victor Larsen, and Prof. Mark Polyphase. And then HLOC is integrated with SuperGlue, a graph neural network for feature matching that I developed when I was at Magic Leap in collaboration with Daniel Detone, Tomasz Madrivic, and Andrew Rabinovich. So HLOC and SuperGlue actually reached the first place in a total of 6 localization challenges. 2 of them were at CVPR 2020 last June, and were similar to here about local features and handheld devices. And this week at ECCV, we won 4 challenges. One was organized by the workshop on map-based localization for autonomous driving, which took place last Sunday. And we also won all 3 challenges on this workshop, which will be the focus of this talk. So with a single pipeline and a single trained deep networks, we won the following challenges. The first is on handheld devices. It evaluates localization.
Paul, yep. Sorry for interrupting you. There's some background noise, I think. Something rubbing.
Is it?
Like
okay, sorry. Let's hope that this works better. Thanks. So on handheld devices for images taken by consumer devices in indoor and outdoor environments with InLoc and Aachen Day Night. Then there's a second challenge about autonomous driving, which requires some robustness to changes of weather, season, and time of the day, with 3 datasets, robot cars, CMU, and CELDA, all recorded with multi-camera rigs. So for example, here we have the left, rear, and right camera recorded on a car. And we have to match, for example, between some kind of summer and snow weathers. And then there's the local feature challenge, which assumes perfect image retrieval and benchmarks local features on the same Aachen dataset. So last year, we also won this challenge, some of them, using hierarchical localization, which is based on our CVR 2019 paper, where we showed that we could actually leverage deep learning for both image retrieval and matching by predicting global descriptors and local features with a single CNN, and doing this for both database and query images, and then offline building a structure for motion model. And for the queries, then we could retrieve some relevant database images, cluster them based on the co-visibility in the map, and then match the local features to estimate a pose from the 2D, 3D matches. So this year, the core of our current solution is SuperGlue. It's a graph neural network that estimates matches between local features in 2 images and reject unmatched points at the same time. So it nicely combines deep learning and optimal transport and can successfully match image pairs with extreme baseline in near real time. And so we showed in this paper that we could obtain very good pose estimation, and they worked both for classical and learned local features. And so we presented SuperGlue at CVPR last June, and we showed great generalization for both outdoor and indoor environments, where you can handle different cameras, image sizes, aspect ratios with a single trained model. And this is very well suited for visual localization. So you can actually find the paper, the open source code, and the recordings of our CVPR talks at this link. Complementing SuperGlue now is HLOC, a toolbox for structure for motion and localization, where from a set of images, we can reconstruct a sparse 3D model using any local features, and then we can localize a given query into this 3D model, resulting in a 6 degree of freedom pose. So we can briefly look at the task of 3D reconstruction with HLOC, where for a set of images, we can extract local features and match them. And then we can run structure for motion, for which we use the incremental mapper in CoMap. And since we need to decide which image pairs to match, we could do it for all images. That's called exhaustive matching, and that's quite slow. Or we can restrict the matches, the matching to images that are visually similar using image retrieval. Or even better, if we have GPS information, we can only match images that are spatially close. Of course, all of this is already implemented into CoMap or in other structure for motion pipelines. So why do we actually bother adding another layer on top of that? Well, CoMap only supports SIFT, while with HLOC we can support several recent deep learning based local features like SuperPoint or D2Net, or even matchers like SuperGlue. And since all of this is implemented in pure Python, it's extremely easy to add new local features and new matchers, and it makes it very easy to prototype. If we're given prior camera poses in a 3D model, for example, from LiDAR alignment, SLAM, or for competitions where we have ground truth poses, then we can also generate image pairs using composability and triangulate a new model with our favorite local features or matcher. And finally, to localize a new query, we extract the features, we can match them, and then lift the 2D matches to 3D using the 3D model. And we estimate a pose with PNP and RANSAC. And again, we can use image retrieval to select the image pairs, and we obtain our previous hierarchical localization framework. And one nice thing is that with HLOC, we can also localize multi-camera rigs using a generalized PNP solver, which is actually very useful when localizing robots or headsets. So for the current challenges, the process is as follows. We first match each query image to up to 50 relevant database images, sometimes less, using SuperGlue matcher and the SuperPoint local features. And then these 2D matches are actually lifted to 2D 3D using either a triangulated structure for motion model for outdoor scenes, as we described previously, or using given 3D LiDAR scans for indoor scenes. And so HLOC supports several data sets from visuallocalization.net and included the ones in this challenge, which are Aachen, Robot Car, CMU, SILDA, and INLOC. So for the autonomous driving data sets, and particularly the Robot Car, CMU, and SILDA, we can leverage the fact that images are captured using multi-camera rigs. And we use, so basically for a rig, for example, we have the left, the rear, and the right image, and they're all taken at the same time, and we know the relative poses between these. That's a rig. So in our case, we use the implementation of low MSAC and generalized P3P solver that is provided by Vald et al. And they have a public implementation on GitHub. However, there's a catch, is that generalized solvers are extremely sensitive to miscalibration. If you have an offset of a few centimeters in the relative poses between cameras in the rig, then that can result in a shift of tens of pixels in the image space and make the pose very inaccurate. So in our case, we re-estimate the extrinsics of all 3 data sets using the reference models, simply using rotation and translation averaging. And we observed that multi-camera localization really increases the robustness in hard cases, for example, at night. It can, for example, also, so here we have some results, for example, on robot car, where there's a reasonable improvement using multi-camera localization. It also better constrains the pose. For example, in this case, the matches are estimated for this rear camera that correspond to features that are very far away. So they provide very little constraint in the direction of the road. Whereas if we use at the same time the left image, then we have additional constraints. Another thing that we had to adapt is for indoor scenes. Turns out that image retrieval is really hard indoor because all the corridors and rooms have similar doors and furniture, and there are very few large-scale indoor retrieval data sets. So we're mostly using retrieval models that were trained on outdoor data. So to boost retrieval indoor, we use some kind of temporal consistency, where in the data sets, since the queries are ordered and they belong to 2 floors, we can first localize easy queries, save the floor, and then deduce the floors of hard queries that are temporally adjacent. So finally, we can use basically this prior of which floor the image was taken to restrict the retrieval of the hard images. And this helps, for example, in this case where we have a query image here, and this is the retrieved images without the temporal consistency, and that's wrong. It's in the wrong building. It's not the same location. Whereas if we have this temporal consistency, then the retrieval is correct, and we can, and then the matching can finally succeed and estimate a correct pose. So now we can look at the results, starting with the autonomous driving data set. We evaluate the localization accuracy on CMU, robot car, and SILDA at 3 thresholds of distance: 25 centimeters, 50 centimeters, and 5 meters. And so in yellow, that's our winning entry from last year, CPR 2019. In green is the 3rd place of this year's challenge. In blue comes the 2nd place capture that is based on our R2D2 local features. And finally, in red is HLOC with SuperGlue. So it provides a reasonable improvement, especially in difficult cases, for example, robot car night. And that, yeah, that allows to win this track of a challenge. We can look at the results and see that, for example, in CMU, it reaches almost 100% at all thresholds. So it's very close to being solved, I think. On the robot car day, it saturates, even though it's not so difficult, seemingly. Maybe there's some issues with the ground truth that is maybe a bit inaccurate. The night data is very difficult. It still poses a lot of challenges, and I think that's mostly due to the heavy motion blur. And finally, on SILDA, the performance is very poor, and I think that might be due to the very large distortion of the images. And this specific camera model is not very well supported in CoMap yet. Now looking at the challenge on handheld devices, again, HLOC and SuperGlue works well for both indoor and outdoor environments with a single model and pipeline. And while other maybe competing methods leverage information that is specific on some environments. So some will work better at outdoor but less indoor. Some are also based on semantics, which also depends on the type of scene. And lastly, the local feature challenge, where HLOC and SuperGlue is as good or better than all competitors, although the performance is saturating a bit. So now that we've seen that, it's also interesting to think about future research directions, and maybe that might resonate with the previous talks. So where can we actually improve performance on these data sets? What should researchers work on now? And that's my personal list drawn from experience on these data sets. First, I think we should strive to go beyond 2D key points. How can we combine for robustness of key point-based localization with the accuracy of direct image alignment, and how to do so in an efficient and scalable manner. So this is a nice figure from Germain et al. From ECCV this week, where I show that few errors in terms of the detected key points can result in large errors in the pose, especially in translation, and that detecting repeatable key points is a very difficult task across conditions, especially with the noise. Next is image retrieval. So here, image retrieval is often a bottleneck. We needed to retrieve a lot of images or to leverage temporal consistency. So how do you actually improve it? Is it just about having more data, and then the mapillary street scene dataset might bring some nice improvements there? But there's also other environments that are unsolved, like indoor environments. And lastly, can we try to better leverage sequential information? Right now we're localizing only single queries, sometimes rigs, but still independent rigs. What is the best approach for localizing sequences? So I think that HLOC provides a good framework to integrate all these improvements and to evaluate them on the standard datasets. So it makes it quite plug and play to evaluate that. And maybe to conclude, I presented our localization pipeline based on SuperGlue and HLOC, which is a simple and clean toolbox for visual localization. You can do a number of pretty exciting things with it. For example, obtaining state-of-the-art localization accuracy on a number of public benchmarks. Maybe you can even try to win the next competitions with it. You can also localize with datasets you have collected yourself by running instructor for motion with SuperGlue. And of course, for your next paper on local feature matching or image retrieval, you can maybe evaluate localization with HLOC within a few minutes of setup, which is perfect for stressful conference deadlines. And lastly, you can of course experiment with new localization pipelines and easily debug them. And all this is open source, pure Python with a number of community contributions. And you can of course find it at this link. So that's it. I welcome your question, and you can also reach out to me on Twitter or by email. Thank you very much for your attention.
Thank you very much, Paul-Edouard, for the great talk.
Thanks.
Are there any questions from the audience? If yes, please use the Q&A box. In the meantime, so I had one question. You partially answered yourself, which was you're using camera rigs, but not sequences.
Yes.
What's the missing part? So what do you need to go from individual rigs, images captured at the same time, to images captured at different times?
Well, if we assume that the rigs are fixed, we can know the relative poses between the cameras in the rig, right? Using the ones provided in the dataset or estimating them from the reference model. In the case of sequences, we don't really know the relative poses between the actual different rigs different times. So this is difficult. We could use visual odometry, but I think that would not be accurate enough to simply run the generalized pose solver as we did for rigs. So that involves more challenges to really find the best way to optimize over different temporally adjacent rigs. And that's something that I don't think there's a perfect solution for that right now.
Yeah, that makes sense. But I mean, potentially you could run like a multi-camera rig SLAM system, especially if you saw the benchmark itself was constructed with images taken about a meter apart.
Yes.
But there's still access to the original datasets, which have a much higher frame rate. And this could actually help running odometry, that you really just run odometry on all frames.
Yes.
And I think the robot car dataset might even provide like a standard odometry solution, not just visual odometry.
Okay, yeah, that's very possible. I would also expect on some sequences maybe some kind of direct SLAM to also work pretty well. especially if we have high frame rate data. Then the question is, how do you actually optimally fuse this temporal information and the kind of sparse information that you get from localizing the actual queries? Because of course, some queries will be easier to localize than others. So you need to find the best combination, I think. And that might require a bit of tuning.
Yeah. In the meantime, we actually have a couple of questions from the audience. So the first one is, hopefully this question will not start holy wars, but what's the main difference between capture from Naval Labs and HLOC?
That's a good question. So as far as I understand, capture is mostly and first a data format that tries to unify the different localization data sets. In our case with HLOC, we assume that we use the COLMAP format for the models, and then images are in a simple folder. So we're not really trying to recreate our own data formats, but rather try to bootstrap what's already out there. Then I think that capture also provides some localization primitives. With HLOC also, it's a bit different. But I think that the main advantage of capture is really the unified data format. That might also be very useful for HLOC at some point. I think that would benefit everyone.
Maybe as a follow-up, so thank you very much for making this whole HLOC pipeline available. How open are you to contributions to the community? Could we use this as a starting ground to build like a reference, like to add building blocks to your reference pipeline?
Yes, it would be. Would be very open to have contributions. Right now, we mostly had bug fixes and minor new features, but I think that even improving the pipeline, adding new alternative approaches would be very beneficial. And I think that it's really designed to be open that way, and I think that community contributions are very much welcome at all levels.
That sounds great. Thank you very much. We have one final question from the audience. Thanks for the great talk. How do you think about multi-view setting for SuperGlue?
Multi-view setting for SuperGlue.
Yes.
So maybe instead of doing two-view matching, actually matching triplets or different views. Well, I think that would be possible, and I think that would definitely maybe improve our results, because of course with two view we have some constraints, and there's some matches that appear good from the two view geometry, but that actually end up being pretty wrong when you add three views or more, because the depth actually disambiguates some. So I think that would be possible. There would be some issues in terms of scalability on how you actually propagate information and context across images, but I think that would be a very interesting future direction. That would probably also improve results.
Okay, great. Yeah, thank you very much for this great talk.
Thanks a lot. Thanks for the questions also. And yeah, if you have other questions, feel free to reach out. Thanks.
Great. Okay.